Hey everyone, welcome back to another topic revision video on CIE A Level Physics. Today we're going to talk about dynamics, and since we won't be able to finish the entire topic in a single video, it's the first part that we are going to focus on, which is the linear momentum and Newton's laws of motion. But before we go into the momentum and Newton's laws of motion, there are certain things that we need to uh, revisit first. First off, mass. We all know mass, that it's a measure of quantity of matter. However, that is also mass is a property of an object that resists change in motion. Now, this is the definition that the examiners are looking for in A-level physics, because we're talking about dynamics now. We're not talking about the quantity of matter anymore. Since this is related to force is equal to mass times by acceleration, we want to know how mass comes into play there. So it's a property of an object that resists change in motion. Now, you might think that this is very reminiscent and very similar to the definition of inertia. That inertia is also the property of a matter that uh, quantifies, or sorry, it describes the resistance to change in motion. But yes, actually, mass is the measure of a body's inertia. So yeah, so basically, this is the resistance to change in motion. And mass is a measure of an object's inertia. That means more the mass, more resistance to change in motion. So more mass implies more resistance to changes in motion. Now, a question then comes up. What do we mean by change in motion? By change in motion, we mean acceleration, acceleration or deceleration, because those are the things that change the motion. So it's either acceleration or deceleration. Technically, deceleration is also acceleration, but you can put that over there. So instead of change in motion, you could say acceleration also. Oh, sorry. So that resists acceleration. So either way, you can do that. Now, mass, we know that it's a scalar quantity. There is no doubt about that. And we also know the unit for this. We already talked about it in the first topic. That is the kilogram. We are talking about the SI units, so kg is the way to go. Next up is the concept of balanced and unbalanced forces. These terms are not as used as much, but in some books, the Newton's laws are described in the form of balanced and unbalanced. So before you run into some trouble and start Googling it, you should know what that means. So balanced forces means, so balanced forces refer to a situation where net force, sum of all forces, or in short, resultant force, acting on an object is zero. Okay, so that's a situation where the sum of forces is zero. This is going to be an important point in Newton's first law. Unbalanced forces mean refer to a situation where, I'm just going to shorten it now, net force is not zero. So that means net force is not zero. We already know that force causes a change in motion, or it can cause deformation. We already know this from IGCSE. So if the net force is not zero, that means one of those things will happen. So we know force causes change in motion, in short, acceleration, or causes deformation. This is some of the possibilities that force can do. Since we're strictly talking about the change in change in motion, we're going to focus on that. So if there is an unbalanced force scenario, there is going to be a change in motion, or in short, there is going to be acceleration or deceleration happening. And if the resultant force is zero, that means there will be no change in motion or no acceleration. And this concept is the basis of Newton's first law. We will come back to that in just 1 second. Before we dive into the Newton's law, one more definition there and we're done. Linear momentum. Linear momentum is a product of an object's mass and its velocity. Notice that we are talking about velocity, not speed. So we are also considering the directional part of that. So linear momentum is denoted by P. So the formula for that is P equals to mass times by velocity. So this is going to be a vector quantity. That means the direction of velocity is going to be the direction of momentum. Units. It's fairly easy. There's nothing about it. So this is kg meters per second. Now, there is, since we are going to be talking about change in velocity, acceleration, we already are familiar with this from kinematics also. So similarly, What about the change in momentum? Right? So change in momentum, basically it will have the same units, but it will be caused by, since we are assuming mass is constant, this is going to be mv minus mu. Basically momentum after final moment, you can say final minus initial, basically final momentum minus initial momentum. This also simplifies to mass times by v minus u, which could translate into mass times by change in velocity. Now, what this implies is that the change in momentum occurs in the same direction as change in velocity. And we know what change in velocity represents. Change in velocity represents acceleration. So therefore, direction of change in momentum is going to be the same as direction of acceleration. So this concept is going to be important in the Newton's second law. Now, this was the scenario where we had constant mass. In most cases in mechanics, we will be dealing with constant mass. But there could be cases where you're dealing with changing mass, non-uniform mass, but constant velocity instead. So you might find certain examples in rocket propulsion, where mass is being changed because of the burning of fuel, but the rocket, if it's moving in constant velocity, there's still going to be a change in momentum. So change in mass due to fuel burning, but rocket could maintain constant velocity. I've forgotten, this was one of the MCQs in recent years. I've forgotten whether this was in 2024, 2025, or 2023, but it was somewhere very recent. So in that case, what we will do, the change in momentum would be the change in mass times by v. Simple. The end result would be the same, the change in momentum. Right. Now that we know a little bit about these concepts, we can talk about Newton's laws of motion, because they are going to state the same things that we have just described about. But we will revisit them again, obviously. So, first law states that a body continues at rest or constant velocity unless acted upon by there are different variations to this. You could say external force, you could say unbalanced force, you could say resultant force. You will find different variations of these words in different books. All of those are fine, but this is the most favored one by examiners. External is also fine, but resultant force is more favored. Even if you don't write this, even if you just say force, that still means that you're talking about the same thing. Now, what are the points to note over here? We actually already talked about them right over here. Is that resultant force basically means sum of forces, which is basically we represent this with a capital sigma F, sum of forces. So that means it's not just one single force, it's the result of sum of forces, or it's actually, sorry, the result of multiple forces. So the first thing to note is that when a body is under uh, sorry, no, my bad. Sorry. A body or an object requires a resultant force or just a simple force to cause a change in motion. So that means either it will stay at rest or like it will just moving with a constant velocity unless there's a cause for change in motion. Either it will accelerate, it will decelerate, it will come to a stop, or it will go from rest to go. All that it requires is a resultant force or just a force to just cause it to change in motion or accelerate. So without the absence of resultant force, the body will have no change in motion. So in the absence of a resultant force, an object will not change its state of motion. So either it's at rest or continues moving at a constant velocity. Now, the second law. In second law, it says that the rate of change of momentum of an object is equal, even if you write sorry, directly proportional, that is still perfectly fine. Okay, so that is still perfectly fine, but equal is now more accepting. To the resultant force applied to it, and there was one more statement. Yeah. So this resultant force acts in same direction as the change in momentum. Or acts in the direction of change in momentum. Either way, both of those wording would be fine. So acts in the direction of the change in momentum. Either way, that's fine. Basically, this is just one statement over here. In some books, they actually don't write this as a period, they start with that. So, and resultant force acts in the direction of the change in momentum. In earlier books, you might find it even this word missing. So, and acts in the same direction. Uh, so, what is acting in the same direction? So, the change in momentum and the resultant force, they are in the same direction. So, let's dissect this now. That the change in momentum has a magnitude and direction because that is also a vector quantity, momentum minus momentum. So the change in momentum, delta P, assuming that we are talking about a constant mass, and most of the time we will be, it's going to be mass times by change in velocity or mass times by change in velocity. When we apply the rate quantity, this basically means we are talking about a time parameter also. So if you notice this particular part over here, the delta v over delta t is your acceleration. So the rate of change of momentum is your mass times by acceleration. And according to the Newton's law statement, is that the rate of change of momentum of an object is equal to the resultant force. So basically, your resultant force is ma. Or you can also write it as F is equal to ma, but you have to remember that this is your net force, not just any force, it's your net force. So this is net force or resultant force, either way, whichever way you want to write. So this follows the same principle over here. So whenever there is a resultant force, there is going to be an acceleration. When there is no resultant force, there will be no acceleration. So these two things are directly proportional to each other. Now, the third law. Third law is quite frankly quite misunderstood by most A-level students. They think it's very simple, but it's actually very deep about that. So to write a more detailed version of that statement, it states that when one body exerts a force on another body. The second body simultaneously exerts a force on the first body that is equal in magnitude but opposite in direction. Now, this is the statement of the third law. An action has an equal opposite reaction. You could see this in books also. This would technically be fine, but has an equal but opposite reaction. So technically this is fine, but you have to understand the third law to be able to describe it this way. So basically what it says, both of these statements says, that there is an action force when one body exerts a force on another body. This is your action force. Let's call it action force. Then there is a reaction force where the second body simultaneously exerts the force on the first body. So basically this second one is your reaction force. So magnitude wise they would be equal, but they would be opposite in direction. So we often call them Newton's third law pair, or we can also call them action reaction pair. Now this could occur in two forms: contact, like in the case of contact forces, and in non-contact forces also. So contact forces, for example, when there are two bodies uh, colliding with each other or interacting with each other. So this is body A, this is body B. Body A exerts a, oh, sorry, no, no, no. Body A exerts a force on B, we'll call that FA, and body B exerts a force on body A, like this. So they will be equal in magnitude, but direction wise they will be equal. So we can say that FA would be equal to minus of F. So this effectively describes the magnitude and the direction part. But what about the non-contact forces? For example, the gravitational forces, electric forces, they exert non-contact. So there is, for example, mass 1, mass 2, they exert force on each other. So M2 exerts on mass 1 and M1 exerts a force on mass 2. Direction wise they're opposite, but they are magnitude wise the same. So there are the same kind of forces also. So it's not going to happen that you have a positive charge over here and you have a, for example, negative charge over here. This uh, positive charge exerts a force on negative charge, right? Sorry, my bad. I did not mean to make one line over here. So both of these are unlike charges. So both of these charges are attracting each other. So these both are electric forces. So these are electric forces. They may have gravitational forces in between also, but the reaction of an electric force is going to be a electric force also. So reaction of an electric force is an electric force also, meaning forces are of same kind. Another thing you must notice from the, especially the contact example, that these two forces are acting on different bodies. So forces are acting on different bodies. So the body A is not experiencing the two forces at the same time. It's A is exerting a force on B, B is exerting a force on A. So the points to note over here. So we already know that the forces are of same kind. Forces act on different bodies, and uh, have equal magnitudes but opposite direction. Now, let's take a look at some example scenarios. Uh, Actually, no, wait. No, wait. Let's discuss weight first before we look at some examples and then some past year questions. So, uh, we know what the difference between weight and mass is. So, weight is the pull of gravity on a mass. You could also say the gravitational force acting on the mass. So weight is basically a force. So we already know that sum of force is equal to ma, or like F is equal to ma. So that means what should be the weight? So how should we quantify the weight? We already know that this actually sounds like this, but how do we actually make sure of this? So let's see an example scenario. Actually, um, cases of example cases of motion where we need to apply Newton's laws of motion and the forces principle. So first, let's talk about the object under free fall. So let's say, for example, an object has mass m and it's falling under gravity. There is no other force on it. So according to the Newton's second law, sum of force equals to mass times by acceleration, and this force would be the weight on this. But we don't know whether it's equal to mg or not, but let's say anyway. So weight, which is the this ma, because this is the only force acting on the body. There's no result. There's no air resistance. Sorry, no air resistance. No air resistance. So we know weight is mg and this is ma. So when you cancel out m and m, that means your acceleration has the same magnitude as the g, acceleration due to gravity. So objects under free fall with the acceleration due to gravity because of this principle. We studied this in kinematics also, the acceleration due to gravity. The acceleration due to gravity is equal to 9.81 because of this, because weight is the only force acting on this. But what about there is an air resistance in it? So object under free fall with air resistance. So what will happen now? So same thing. We will draw a mass. This is weight. This is object m. The body is falling downwards, so the resistive force would be opposite to the motion. So the net force equals to ma as a consequence of Newton's second law. So net force, since the motion is downwards, we would do W minus R equals to ma. Okay, so this is how the case is going to be depending on what's exactly happening. So we will come back to this in a while, but this means that because of the effect of the resistive force, the air resistance, the acceleration would be less than g. Let's actually see that anyway. So this is mg and this is, sorry, minus r equals to ma. So this already effectively means that your a is less than g. So mg minus ma equals to r. G minus a is equal to r over m. Since we have air resistance, this means that the g minus a would be greater than 0 and g would be greater than acceleration, or acceleration would be less than g. So acceleration would be less than z in air resistance. This is a fairly simple conclusion to make over here, but a certain question often comes, uh, although we will actually see this in the terminal velocity case also. There's an important aspect to it that students often uh, make a mistake on. And this is actually related to the kinematics also. So let's draw a line over here because we're going to talk about the same thing. First off, let's see how the velocity time graph would look like. So velocity time graph for both of these would look like this, Vt. So if the object is like falling under gravity, whether it's falling from initial velocity, or let's say uh, let's say this, for example, and this could be, sorry, right, okay. So this would be the case with u is equal to 0, fall from rest, and u not equal to 0, falling from initial velocity, some velocity, whatever this is. So this is your u, this is your origin 0. We already know that the gradient of velocity time graph would represent air resistance. But if there is no air resistance, if there is no air resistance, the acceleration would be constant. This would be this way. However, how will the graph of a, sorry, I should have made it black. Let's make it black. Vt. So it will go like this. It will continue decreasing. Why? There is a reason for that. So air resistance increases with speed. So because the object is accelerating, air resistance would increase. Since object is initially accelerating, air resistance will build up fast, or would build up fast. But due to that buildup of air resistance, the net force will decrease. So due to that, net force would decrease, and that would reduce acceleration. So reducing acceleration. So that means the gradient of the graph would go this way. An important question that comes up, let's say an object is falling in air. So an object falls from a height of, let's say, 200 meters from rest, and another identical object falls from same height, sorry, in air. We're going to even increase that also. So let's go with 1,000 meters, for example. Actually, the distance is inconsequential. It's just there to show the difference. The question is, which object will take longer? Will take longer to reach the ground. To answer that, we can actually look at this thing, the graphs. So if we redraw the graphs, actually we can do this over here. I will make a different graph for this. So if this is initial velocity fall from rest without air resistance, and this would be the graph with air resistance. And we know that displacement is the area under the graph. So notice one thing which is fairly obvious. This one, since it has higher values for some portion of that time, it will achieve that displacement faster. So the area under this thing would be achieved faster. The other case, this one for example, let's draw it this way, it would take longer to achieve because the values are decreasing. So the same thing would actually come maybe somewhere over here because it's all about area, right? So that's why since you can also say that it is decreasing, it's reducing velocity, so it would take longer. But from the graphical perspective, the area, because of its decreasing values, the area would sum up to 1000 meters a little bit slower. Now, let's extend this case to when the object is thrown up in air. So object thrown up in air and falling back. So we actually saw the velocity time graph without air resistance in the kinematics topic, in the projectile also. So without air resistance, it would look this way. So this is without air resistance. A would be simply equal to G. We already know this, but what happens with air? We know, we actually saw this on the left side also. So for example, if it's going up, the weight and resistance would be going up, going this way. But when it is going down, the forces would be opposite in motion. So when it is going up, it will decelerate faster. So because you have weight, so actually the displacement is going up. So this is minus weight minus r equals to m a. So this is your mg, and this is your r. This is your a. So as you can see, a is greater than the g itself. So it will decelerate faster. So it would decelerate faster this way. And also the fact that the resistance decreases with speed. So when it decelerates, R would become smaller, then the resultant force would decrease also, acceleration would get lower and lower. So as you can see, the acceleration is also decreasing. But what happens when it's coming down? So coming down basically would be the same case we saw over here, and we just need to redraw this on the opposite direction. So basically this would be this way. So roughly going this way if we redraw this. Right. Yeah. Sorry. No. Somewhat like this. Somewhat. It's actually not a straight curve. Actually, the gradient will be changing. So this is all you have to remember, basically. So this is with air resistance. And when it flatlines, this is where the terminal velocity happens. All right. Okay. All right. Right. Object sitting on ground or resting on ground. Actually, it should have been resting. So if you have an object that is sitting on the ground like this, notice two things over here. Object has the weight, definitely, but what about the contact forces? What about the reaction forces? So reaction forces or normal contact forces exist in pairs. That means the Newton's third law pairs or action-reaction pairs, whichever way you want to call it. So this means that the since the book or the object is exerting a force, let's call it a book, for example, is exerting the force on the ground, there will be an equal, actually, sorry, should be point of contact. And the ground would be exerting an equal but opposite force on the book. So FB is the force on ground due to book, and Fg would be the force on book due to ground. Now the key word over here is the force on the book. So there are two forces on the book. So forces on book include weight and reaction force or normal contact force. So normal reaction force. So this means that if we want to find the sum of forces on book, you will see that this is sum of forces equals to MA, which is going to be W minus, let's call it R for simplicity. You can call it N also, either way, MA. Since acceleration is 0, this would imply that W is equal to R, or W is equal to R, that the normal reaction force is equal to weight. So this was the case when the object was stationary. But what if the object is on the ground, but it's accelerated? So sort of like a lift example. So this was the third case, fourth. Right. So object, let's say in an elevator, and it's accelerating upwards. So this would mean that, for example, you have the same scenario. This is the object. This is the reaction force. This is the weight. The system is going upwards. This is the acceleration going upwards. So since the acceleration is upwards, you would actually write it this way, ma. sum of forces equals to that. So in that case, you would notice that the reaction force is equal to MA plus weight, which is your mg. So m, this would be A plus G. So effectively, R, which is often written as the apparent weight on the object, is actually uh, more than the original weight. So it will be like squished down. So when you're going up the lift, you feel that there's a your weight has increased. Suddenly you're falling down. Basically, that's because that the net acceleration that you're going through because of your apparent weight has increased. But what if the same scenario is reversed? So object in elevator accelerating downwards. So same scenario, similar scenario. We have the ground, we have the object. This is weight, this is R. Acceleration is now downwards. Since the acceleration is downwards, we will write it as W minus R ma. So in that case, when you rearrange, you would see that R is now W minus ma, or mg minus ma, and this would be mg minus a. So this is your R. That means your apparent weight is lesser than actual weight. So you will feel lighter. A person would feel lighter. Feels lighter going down. A special case of that. What if um, acceleration becomes equals to g? So what will happen then? So same principle over here. Basically, yeah. So you have mg minus r equals to mg now. So this cancels out. So basically r is 0. That means you have no weight. Apparent weight is 0. That means this is the state of weightlessness. And this is the time when happened when you're falling under gravity or acceleration due to gravity. However, in all these scenarios, you have to remember that R is the force exerted, sorry, by ground on object. But there would exist a force downwards also on the ground, or not on the object, on the ground. So a similar but opposite force would act downwards on ground. So if the question comes, what is the force exerted by the ground on the object? That is the clearly obvious, this one, but what is the force acting by the object on the ground that is also similar but acting down? So that will have the same magnitude as your normal reaction force, but it would be acting down. Now, this is not the only case where this is we are going to be using that. So, fifth case, an object lifted by a rope, string, rope, whatever this is. Similar scenario would happen. This is the, for example, rope or a string. The object's weight would be acting downwards, but the tension would be upwards. Tension is always away from the object. So, right. So depending on the direction of acceleration, whether it's going this way or going this way, it would dictate the signs of the motion. So for example, if going upwards, it would be T minus W equals to MA. And if it's going downwards, it would be W minus T equals to MA. So just like the previous example, going up, tension would be higher than that. That means you would actually need more force than weight. This is a mathematical way of saying that. And if you're going downwards, the tension would be require less weight than mass. So yeah, basically that's it. Right. Okay. All right. Certain examples where we also have to deal with graph of momentum, um, time, what that gives us. If this is momentum and this is time. So can you tell me? So we know momentum is mv basically. So if you have a graph like this, what will it give us? So students, if you have thought about it, that's good. The gradient of the momentum time graph gives us change in momentum over change in time. So obviously this is your force. But what if you have force times by force time graph? So force time graph. So let's say you have this force time graph. So can you tell me what is going to be the gradient and the now? So gradient area. So gradient is your change in force over change in time, and area is the whatever, if you're doing an integral form or whatever, this is going to be the total change in momentum. So gradient is not so the gradient of force time graph, that is not uh, in our scope. So and we won't be even using that. So just like the area of the momentum time graph, we don't need it. We just need the gradient of momentum time and the area of the force time graph. So change in momentum is your mv minus u. Right. Okay. So let's try out some questions to nail this topic. Okay. So let's see the MCQs first. And a ladder is positioned on icy, frictionless ground and is leant against a rough wall. At the instant of release, it begins to slide. Which diagram shows the direction of P, W, and R acting on the ladder as it slides? Now, a common mistake students actually made in this is taking P and R to be the normal reaction forces. So they're not strictly just normal reaction forces. Since the ground is frictionless, R is the reaction force because there is no other force acting. But P, on the other hand, P is the sum of two forces. The wall, since it is sliding down, the wall is offering friction upward. The normal reaction force, let's call it N just for the time being, would be this way. And remember, we call it normal because it's always normal to the surface. So the resultant force of these two would be in this direction. So these two would cancel out. So we have to choose from this one since the ground itself was frictionless. So there is no force in this direction or this direction. So the R force direction is correct, vertically upwards. So B is the correct answer. Right. The stationary ball of mass m is hit by a bat. The ball leaves the bat with a velocity v. The bat is in contact with the ball for a short time. Right. What is the average force on the ball? So force on the ball is rate of change of momentum. So what is the total change in will momentum? So m is as it is, final velocity is v, initial velocity is 0, divided by short time t. So basically just mv over t, which is this one. Right. Terminal velocity, we'll look at it. This one. Right. Okay. So a lift elevator consists of a passenger car supported by a cable that runs over a light, frictionless pulley to a counterbalance. Counterbalance falls as the passenger car rises. Some masses are shown in the table. What is the magnitude of acceleration of the car when carrying just one passenger and when the pulley is free to rotate? Okay, so over here we have to find out what's the sum of forces. So when you add up the total weight of the passenger car and the passenger, this would be 600 G. Right. And similarly for the counterbalance, it would be 640 G. The tension is going this way, we already know that. But how do we solve this system of connected bodies? We know that the acceleration they will share, that would be the same, and in which direction, this is also obvious because the counterbalance is heavier. So there are two second law sum of forces equations. For the counterbalance, you have 640 G minus tension equals to mass times by acceleration, 640 times by A, in the direction of acceleration. Similarly, tension is going this way now, the motion is going that way. So tension minus 600 G equals to 600 A. Now let's solve these simultaneously. So you have 640 G minus tension equals to 640 A. And the tension is positive in the second equation. This is negative. And this is 600A. So we just need to add these equations together, not subtract them. This already cancels out. This is 40G, and this becomes 1240A. So acceleration would be 40 times by 9.81 divided by 1240. So 40 times by 9.81 divided by 1240. So this would be 0.316, which is this one, B. Right, okay. We will cover the collisions later on. also for this one. Okay, a ball of mass 2 kgs travels horizontally with a speed of 4 meters per second. The ball collides with a wall and rebounds in the opposite direction with a speed 2.8. So basically what's happening is that this is the wall and this is the object. This is the object. The initial velocity is 4 and v is 2.8 in this direction. So if we consider this direction to be positive, u is going in opposite direction. So change in momentum is mv minus u. This is going to be 2.8 minus 4 because considering that that is all in the opposite direction. And if you divide by time right over here, this is going to be 115 milliseconds, so 0.15. So you have 2 times by 2.8 plus 4 divided by 0.15. So this is 91. Okay, let's carry on. Right, two identical balls are projected vertically upwards from the ground level with the same velocity. Okay, same initial velocity, right? Ball X is in a vacuum and ball Y is in the air. Which statement about the motion of the balls is correct? Uh, right. Which statement about, okay. All right. So first off, we need to see how the motion looks like. So without air, the velocity time graph. Oh, so without air, the velocity time graph looks like this. But with air resistance, it would be somewhat like this. So what that means is it's going to reach the maximum point. So this is your with air resistance. So it's going, so the y and this is your x. So x reaches a maximum height because you can see the area under the graph for the x1 is greater, so maximum height, greater maximum height. So that means this cancels out this one. Now we need to just justify longer time. So longer time because obviously it's allowed to go at a higher acceleration. So A. Right. Okay. The graph shows the variation of the momentum p with time t for the car. What is the resultant force on the car at t is equal to 10 seconds? Okay, so remember the resultant force is basically the gradient of pt graph. So we just need the gradient of this line because the gradient is not changing in between this. So 20, no, sorry, no. 4 minus 1 over 20. And remember this thing, times by 10 raised to power 4. So 3 divided by 20 times by 10,000. This would be 1500 newtons. Okay. Right. These are basically the okay. A tennis ball is thrown vertically upwards. The tennis ball reaches its highest point, then falls back down to the point to which it is thrown. That means at this point the net displacement is 0. At which point the air resistance is significant. At which point on the part of the tennis ball is the resultant force on the tennis ball greatest? Greatest. Right, okay. At the start, just after the tennis ball is released, when the tennis ball, oh, okay, all right. So basically, this is going to be the same way. Uh, it's going to be this thing, this type of graph. So as you can see, the gradient is highest over here. So this is going to be at the start after the tennis ball is released. A golf club hits a golf ball. The graph shows how the force F on the ball varies with time t. Which graph shows the velocity v of the ball varying with time t? So we know that force is directly proportional to acceleration and it's also proportional to change in momentum. So if from this time to this time there is change in momentum happening over this time, so we all already know that the area under this graph is change in momentum, and we can see that the force is increasing over time. That means the acceleration is increasing. So increasing acceleration, what does that mean? Means increasing velocity. Increasing velocity, but non-uniformly. Similarly, this path, this is acceleration decreasing. So velocity decreasing. So we need to see where this is happening. So acceleration decreasing, velocity increasing. So this, you see, the gradient is decreasing. So we don't need that. We need increasing. So it is increasing and then it's decreasing. So that's B. All right, carrying on. What is meant by the mass and by the weight of an object? So mass is the property that resists its acceleration, and weight is the pull of earth on it. This is straightforward, easy marks over here. All right, a ball of mass 0.1 kg is thrown towards a stationary vertical bat. The ball hits the bat with a horizontal velocity of 20 meters per second. The ball rebounds and leaves the bat with horizontal velocity of 15 meters per second. So that means it's going this way, 15 meters per second. What is the change in momentum of the ball? So change in momentum is equal to mv minus u. So remember, if we are taking this direction to be positive, this would be taken as negative. So this would be 0.10 v 15 minus 20. That means 15 times by 15 plus 20, which is 35. So 35 times by 0.1, that is 3.5. Right. Actually, we already know this, even though we haven't discussed it properly. But let's keep it for the next time. Let's see this. A block is moving along a horizontal frictionless surface. The constant force F and a constant resistive force 5 Newton act on the block as it is moving in the direction of F. The graph shows the variation with time of the momentum of the block. All right, what is the magnitude of the force F? Now, the acceleration on the body or the deceleration on the body, either way, it's happening due to the sum of forces acting on it. So Newton's second law, so basically the F minus 5 is the rate of change of momentum. So mv minus mu over t. So we know that the change in moment over change in time, that gives us the gradient. So basically this is equal to the gradient. So this would be, let's figure this out. 0, no, sorry, this is a 1.5. So 1.5 minus 2.7. 1.5 minus 2.7 divided by 0.4, and then F would be plus 5. So let's calculate this. So 1.5 minus 2.7 divided by 0.4 plus 5, that is 2 newtons. All right. Newton's third law describes two forces that are equal in magnitude and form a pair. Which description of the two forces in such a pair is not correct? They act in opposite directions. That is correct. They act on different objects. They have the same type of force. They cause an object to be in equilibrium. That is not correct. Action-reaction pair don't cause that. So, all right. A car of mass 850 kg is traveling in a horizontal straight line. The diagram shows two horizontal forces acting on the car in opposite directions. One force has magnitude 1200, the other force has 1600. What is the magnitude of the acceleration of the car? So notice that this force is have more, so it doesn't really matter. So if you take this to be the forward force, the positive force, you will get a deceleration, and if you take this one, you will get a still acceleration. Both ways you will get a similar answer. So you have 1200 minus 1600, 850 times by a. So this is minus 400, 850 times by a. So a would be 400 divided by 850, which is 0.47. This is the, and they only asked us for the magnitude of acceleration. Okay, all right. Let's try some paper 2 questions also. Wait a second. Okay, this is a good question. A man stands in a lift that is accelerating vertically downwards. Which statement describes the force exerted by the man on the floor? So remember, we talked about this. They're talking about the action-reaction pair. So you have this. Come on. Right, okay. So the action-reaction pair happens. So from the point of contact, so this is the ground, this is the ball. The ground exerts the force upwards, the ball exerts the force downwards. Technically, they would both be equal to each other. So, and since it is accelerating downwards, if we look at the R over here, which is basically this thing, R, weight, so W minus R is accelerating downwards. So R would be W minus MA, that is mg minus ma. So R basically is less than the weight. So that is what it's telling us. So mg minus ma, so basically, and that would be the scenario. So it would be less than weight. It is equal to the force exerted by the floor on the mat. So as we said, their action-reaction pairs, so technically they would be the same magnitude. So these two would cancel out right away. It is equal to the weight of the man. It would be only in the case when the system is not accelerating. All right, okay. All right, let's try some paper 2 questions. Okay. Define linear momentum. So linear momentum is product of an object's mass and its velocity. All right. A car of mass 1800 kg is moving in a straight line. Figure 2.1 shows the variation with time t of the momentum of the car. Calculate the maximum speed reached by the car. Okay, so first off, we need to just quickly remember. So the gradient of the momentum time graph is basically the force. And momentum is starting from zero. That means velocity is zero over here. We need to figure out what the velocity over here because we have the mass. So momentum is equal to mv. We can actually do this over here. So P is equal to mv. V would be P over m. At the highest point, we have 7.2 10 raised to power 4 divided by mass 1800 kgs. So 7.2 times by 10 raised to power 4 divided by 1800, 40. Calculate the maximum kinetic energy of the car. That is easy. This is going to be, there are two ways to do this. You can do p squared over m, or since we have the maximum speed, you can do half mv squared. Both of the ways we will get the same answer, but just to be sure, you have half. P was 7.2 10 raised to power 4 divided by, this 1800, and this is half. M is 1800 times by 40 squared. So, right, okay, so let's see. So 0.5 times by square of 7.4, 7.2, and 10 raised to power 8 divided by 1800, 144. Okay, now this one. So 1800 times by 40 squared divided by 2. Notice we're getting the same thing. So you can basically do it in two significant figures. So 1, 2, 3, 4, 5, 6. So 1.4, 10 raised to power 6. Okay, show that the acceleration of the car at time t is equal to 4 seconds is 5 meters per second. So 5 is over here. So, yeah, right, okay. So we know the force is coming from the gradient. So what are we going to do over here? So force is the rate of change of momentum. That is the gradient. So if we can find the force, we can find the acceleration. So gradient at that time, so 7.2 minus 0, 8 minus 0. So greatest momentum we actually found to be 7.2 10 raised to power 4. Wait, 8. Right, okay. Divided by 8. 8, was it right? Yeah, okay. And acceleration is F over m. So this would be 7.2 10 raised to power 4 divided by 8 divided by m, which is 1800. So 7.2 divided by 8 divided by 1800 times by 10,000. So this is 5 meters per second squared. Sorry, you can write it this way also. Determine the distance traveled by the car between the times this. So distance traveled by the car, basically we need the velocity. So we already know the maximum velocity. So basically this is 0, this is v is equal to 40, this is 0. So basically we just need the area under the graph. Actually we simply half times by 40 times by 12. That's it. We don't need anything else. So 40 times by 6, that is 240, right? So, so half times by 40 times by 12. So this is going to be 240, 240 meters. Okay. On figure 2.2, sketch the variation with time t of the acceleration a of the car from 0, t is equal to 0 to 12 seconds. Okay, so acceleration of the car at 4 is this. Okay, so force is constant up till this thing. So we have one force over here, the second force would be over here. So we need to find out this force also. So this would be decelerating force, but still um, this would be 7.2 10 raised to power my 4, but 0 minus that basically, and this would be 12 minus 8. So this would be minus 7.2 divided by 4 times by 1000. So this is 18,000. So force in this is minus 18,000, and this was 14 10 raised to power. Oh no, wait a second. Oh no. 4. Wait a second. Force was we didn't calculate the force. We calculate. Oh, this was the force. Okay. So right. So 5 times by 1800 basically. Uh, yeah, 9,000. So this is in this part force is 9,000 newtons. So basically that's all we need. So acceleration, we we found the acceleration in the first half, that was a we where did we find it? Oh yeah, 5 meters per second. Now we need for the other thing. So 5028 would be 5. And now we need for the other one, it would be greater. Remember, it's minus 18,000 from 9,000 to 18,000. So magnitude will be doubled, simply 10,000. And this would be the case. Acceleration, if force is constant, acceleration is constant. All right, okay, moving on. Let's see. Define momentum. Again, it's a product of uh, mass times by product of mass and object's velocity. A child stands on a child stands on a scooter on a horizontal ground. The combined mass of the child on the scooter is 16 kgs. Okay, like this. So this would be weight would be 16g. Child starts from rest and pushes once on the ground with a foot, which causes her to accelerate. The push lasts for 1.1 seconds. Speed of the child on the scooter after the push is 0.6. Determine the average resultant force acting on the child horizontally on the child on the scooter during the push. Okay, so force is the rate of change of momentum or average rate of change of momentum. So total mass is 16 kg, change in momentum is 0.6 from rest 0, and the time is 0. Wait a second. Time 1.1 second. So 16 times by 0.6 divided by 1.1. So 8.727, so basically 8.7. Later in the child in B travels down a slope at a constant angle to the horizontal. At point A, her speed is 0.6 meters per second. She has a constant acceleration of 0.85 meters per second parallel to the slope. After a time of 3.7 seconds, she reaches the point B. Calculate the distance x traveled by the child during the slope. So we have the acceleration, we have the time, and we have the initial velocity. So basically, we just can use kinematics equation of a t squared. So this is going to be x equals to 0.6 times by 3.7 plus half 0.85 times by 3.7 squared. So 0.6 times by 3.7 plus 0.5 times by 0.85 times by 3.7 times by 3.7. Sorry. So this becomes 8.04. You can say it's 8 also meters. Now, at point B, the child in C applies the brake with constant force to maintain a constant velocity. Point C is 18 meters from point B. The work done by braking force is 250 joules. Okay, sorry, this is the energy part now. We will see that in the energy. And this is the collision. In the next video, we will see that. Same thing over here. Let's find a question. This is terminal velocity. We will see when we study terminal velocity. Same thing. Okay. A block is pulled in a straight line along a rough horizontal surface by weighting force X. Weighting force means the acceleration will be non-uniform. A resistance is negligible. Assume that the frictional force exerted on the block by the surface is constant and has a magnitude 2 Newton. So basically 2 Newton is acting, is acting this way. This way. I don't know what's happening. Okay. The variation with time t of the momentum p of the block is shown. State Newton's second law of motion. We already know that the rate of change of momentum is equal to resultant force, and it occurs in the same direction as the force. Okay. Use figure 3.2 to determine for the block at time t is equal to 2 seconds the magnitude of the resultant force on the block. Okay. So at time t is equal to 2 seconds. Okay. So between 0 to 4, the force is going to be constant because the gradient is constant. So 3, 2. All right. So force is basically gradient. So 3 over 2. So that is just simply 1.5. Force X. Constant magnitude. So this was the resultant force. So resultant force is equal to X minus 2. So yeah, X, was it X? Yeah, all right. And 2 Newton, yeah, right. Okay. So, and this is equal to 1.5, so X minus 2. So X would be 1.5 plus 2, so that is going to be 3.5, so 3.5. On figure 3.3, sketch a graph to show the variation of force X with time t from t is equal to 0 to t is equal to 6 seconds. So, right, okay. So over here, in this part, the resultant force has become 0, so that means X will become 2 over here. So over here, In this part, it is 3.5, and then it becomes 2. So from 0 to 4, 3.5, and then it becomes 2. Simple. That's it. All right, let's try this one. A block is pulled by a force of. Wait a second. Isn't that the same thing? It's okay. So same session but different variant. Similar question. Okay. Block X straight line along a rough horizontal surface as shown. Assume that the total resistive force opposing the motion is 0.8 at all speeds of the force. Okay. The variation with time t of the magnitude of the force x is shown. Define force, that is the rate of change of momentum. Okay. Determine the change in momentum of the block from time t is equal to 0 and from 2 times t is equal to 3. So change in momentum from time t is equal to 0. Wait a second. Oh, okay. So total resistive force is this, right? So change in momentum. Oh, wait, sorry, what am I doing over here? Okay, so that is going to be x minus 0.8, and that is the uh, this divided by t. So basically, we need this x minus 0.8 times by t, which is 3 seconds. So x is value 1.4 minus 0.8 times by 3. 1.8. Okay, all right. So, all right. Describe and explain the motion of the block between time t is equal to 3 and time um, 6 seconds. Right, okay. Wait a second. From between time 3 seconds and time 6 seconds. Okay, so between 3 and 6, the x has become 6, 7, 8, and it remains so. So what we need is 0.8, 0.8. Oh, okay. So if it has become 0.8, then x minus 0.8 would be 0. That means acceleration is 0, change in momentum is 0. Then that means change in rate of change of momentum. That means force would be 0 also. So um, x becomes, x remains. Explain the motion. Okay, so it remains constant at 0.8 newtons, reducing resultant force to 0, causing acceleration to remain 0 and velocity to be constant. Or to remain constant, however you want to phrase it. Force X produces a total power. Okay, so this is now energy. Wait a second. Uh, okay, so force X produces the total power of this when moving the block between time t is equal to 3 seconds and time t is equal to 6 seconds. By the way, these sessions are, as I've said before, these are revision sessions. If we are doing other topics in questions a little bit, it's fine. I'm already assuming that you have gone through the syllabus. Calculate the distance moved by the block during this time interval. Okay, so we know that force X is constant between 3 and this. There is no net force over here. So the work done by the X would be equal to the work done against the that also against 0.8 Newton resistive force also. So basically that would be power is equal to Fv, and we need the time, so Fs over T. So power, so S would be PT over F. P is 2 watt, time is 3 seconds, and F was 0.8. So 6 divided by 0.8. Uh, Wait a second. No. Distance moved by the block during this time. Force X produces, that is correct. 2 divided by this. Oh, no, sorry, no. Right, okay, right. The block is at rest at time t is equal to 0. Figure 3.3, sketch the graph to show the variation of momentum of the block with time t. From time t is equal to 0 to 6 seconds, numerical value of the momentum are not required. Okay. So, change in momentum from uh, t is equal to 0 to 3 t is equal to 3 seconds was 1.8, and from 3 to 6 is 0. So basically change in momentum. So this is momentum, not change in momentum, not force. So momentum is changing uniformly, right? So momentum is changing uniformly because velocity is changing uniformly. P is equal to mv due to uh, constant acceleration, constant force. So momentum would be increasing up until what was 3. Let's stop over here. And then momentum remains the same because resultant force has become 0. That's it. All right, so hopefully this was sufficient for you. Let's see each other in the next video. Bye bye.